we want to really maximize our runtime, right? Because worst case means that our runtime is as big as it could be. And so how can we do that? Well, remember that the concatenation runtime, the runtime for concatenating two strings, is actually linear in terms of the number of characters in those two strings. So for example, if I'm concatenating a string of length n with a string of length m, right, then really the runtime is theta of n plus m. And so how can I make my runtime as big as possible using only n nodes? Well, the worst case, right, the worst case is when my n nodes are in a root to leaf path. So all my n nodes are here, right? So I'm just gonna number them like 1, 2, 3, all the way to n. So in this case, when I'm at node 2, I would have done 1 plus 2 character concatenations when I'm concatenating my node's value to the current path. And when I'm at node 3, I would now have done plus 3 for my total concatenation runtime, and so on and so forth until I get to n, which is really just equal to n squared, right? So this is a theta n squared runtime in terms of n, right, worst case. And now let's look at the other example. What if we want to figure it out in terms of h, which is the height of the tree? So again, if we have this root to leaf path, right, then we want to make sure that our root to leaf paths, the number of them, is maximized. Okay, so how can we do that? Well, let's say that our height of the tree is actually h. Like, in other words, it's perfectly balanced, right? So, and it's complete. It's a complete binary tree. So every level, all the possible slots are filled from left to right. Okay. And so basically, I have something that looks like this. And so if my height is h, then at the last level, right, the number of nodes I'm going to have, in other words, the number of leaves I'm going to have, is 2 to the h, right? So this is equal to the number of leaves. And so if I know that I have 2 to the h number of leaves, and for each of them, how much runtime am I doing? Well, I know that I have to concatenate h letters, right, from my root to, sorry, not letters, but basically h, yeah, I guess h string concatenations, right? And so it's going to be from root to leaf, the number of the height of the tree. And so really this is just theta of h concatenations for each of these root to leaf paths, right? And so what happens is that this becomes theta of 2 to the h times h, which is a humongous time. It's exponential, right? Okay, and just one more note on this theta h. I'm just assuming that the values in the tree are bounded by some kind of a constant, right? And so if they're bounded by some constant, then I can say that it's really like theta 1 plus theta 1, whoops, plus theta 1 plus theta 1, etc. And so that's really just h times theta of 1, which results in theta of h. Now you might be wondering, why were we not able to do this balanced, complete binary tree for the case of n, right? Why couldn't we have something that looked like this, where the height is going to be log n? Well, the reason for that is because, let's actually calculate this, right? So at the last level, the number of leaves we're going to have is going to be 2 to the log n, which again is just going to simplify to n, assuming log is base 2. And because we can also bound the values in the tree by some constant, we can again say that it's theta of log n, right? Which is theta of n log n. Whereas before, if we assumed a spindly tree, such that it looked like a linked list, right? All n nodes were like occupying a complete level by itself, then our runtime ended up being n squared, right? Because we had to do 1 plus 2 plus 3 plus all the way to plus n concatenations, right? That was our runtime for concatenating. Okay, and by concatenations, I mean we're actually doing n concatenations, but the runtime is 1 plus 2 plus 3 plus all the way to n. This is actually resulting in a much higher runtime, which is why we choose this as the worst case for the first part when we're talking about in terms of the capital N rather than this balanced complete binary tree. Okay, so hopefully that made sense. And then the next part, which is going to be on iterators, or sorry, red-black trees, is going to be the next video.